Welcome back. This is CET 4333. In this lecture, I want to just finalize the chapter 2. And so the next week, I can go through a bunch of all of your homework problems and some other homework problems from the book. Take a look at those problems and get you ready for your exam. Keep in mind, I posted the exam dates on your drop boxes. It says exam dates, so all exam dates are specified that it's going to be not this weekend, coming weekend, the following weekend, you will have your first exam, and exam dates are posted, all exam 1, 2, 3. In here, in hardware, how do we implement a open collector NAND gate output circuit? Well, established an AND gate, and the output comes in, and here's ground, and the output voltage goes over there. If I have 0 volt, 0 volt, meaning 0 here, 0 here, which means the gate is open. This is the NAND gate. Remember that I'm inverting the output. 0 and a voltage, still I get plus, because of the NAND gate means an AND gate plus an inverter. So V voltage and 0, here V and 0. Again, I get 0, an inverter, so I get a plus volt, which means the output. Then if they both are voltage applied here, then output is 0, I don't get anything. This means open collector NAND. The symbol is this. This is exactly what you have seen in digital course, your first digital course. This is the symbol of AND gate, and if you put a bubble here, that means the output of AND gate is going to be inverted, and we call them by short NAND gate. Here is a wired AND connection of open collector gates. What is happening here, you have two, if you look at it, two NAND gates coming in, and there's a voltage drawing back. So what happens here? Let's say this output of this AND gate, A, and output of this AND gate, B, and here's the wired AND output. The output is going up. So what happens? If this is 0, and this is 0, what do you have here? You have a 0. If this is 0, 1, 0, 1, you still get 0. 1 and 0, you still get 0. Unless you have both of them as a 1, then you will have open system, which means 1. Okay? Here is open collector wired OR bus, the bus that is getting some of them. So you have a NAND gate here, NAND gate here, NAND gate here. The outputs are all connected to a bus. And then you notice that depending on what would be the outputs, these are the gating information, right? Whatever you put in there, in which one, correcting, if this is a 0 and a 0, this is the NAND gate. Then you, based on the output of the NAND gate that we looked at in here, we look over here, 0, 0, you will get a 1. 0, 1, you get a 1. 1 and 0, you get a 1. This is a inverted AND gates output. Then 1 and 1, you get a 0. So this is exactly what happens. Then you can gate one at a time and get all of the information correctly. And again, here is same thing. If we have tri-state gate internal structure and symbol, this is how it is. You put the data here and you put the enabler here. Once the enabler is on, and then you gate the data, and data comes out. So enable is 0 and data is 0. Basically, you have nothing going on. Enable is 0, data is 1, still you get nothing to go on. If enable is 1, data is 0, that 0 is output. If enable is 1, so enable has to be 1, then you get the data out. If you notice that when enable is 1, data and outputs are exactly same. Whatever is in that line, it comes out. In tri-state gate structure is this way. Data comes in and it's connected to an inverter and to another AND gate. Then there's an AND gate here connected to the output of that inverter, and both these AND gates are basically clocked at the same time. As a result, you get the output. So inside the tri-state, this is the gate structure in hardware. And here is the registers connected by a tri-state bus, which means this is a tri-state. So we have a D flip-flops, and then the output of D flip-flops goes through a gate. Basically, I am controlling the output of these D flip-flops. I'm controlling the output of these D flip-flops by having these enablers, keeping them at 0. Once I turn any one of them to 1, then the output of that flip-flop is going to get onto the bus. Can make any register transfers by R of J goes to R of I. Those are the dummy variables. Can't have G sub I equal to G sub J equal to 1. All right? You cannot have that one. So you cannot enable 2 of these at the same time. That's what it said. Violating this constraint gives low resistance path from power supply to ground with predictable results, meaning you get a bunch of garbage. Now, let's take a look over here. You have registers here all the way from R0 to R, whatever it is, n-1. If it is 32 bits, so this would be 32 minus 1, so R31, right? And so you will have in clock here, and clock. And you have a bus. The input from this bus, there's an input to each one of these D flip-flop. Also, the output of each bus, each one of these D flip-flop, it goes to the bus through this tri-state gate. This tri-state basically controls it, right? If there's an input here, I close all these tri-states, so none of the outputs goes to the bus. And this way, for example, you say, example, R1 plus R2 gets to R3. What happens? So R1, you put the R1, all right, and you take him to the an adder, you bring him over here. Usually R1 comes in, you keep him here. There are n bits, so if it is 32-bit thing, you have 32 of this, and then you bring R2, for example, from here, and right to here, then you add them up and you take the results and store them in R3. By having everything, by having everything ready here, you get them in and enable this one goes up and automatically goes to the right register. How? By only taking the clock of that register, that flip-flop. So R2 goes to Y, R1 plus, you see here, concrete RTN, what happened here? R2 went to Y, and then Y added up with the R1, this is R1, Y2, and then the results goes to Z, and Z sends them to R3. So this is how the system works. Now you have to have a control sequence to turn everything on at the same time. So in this situation, you have R2 out on, so meaning if this is R2, meaning this gate is on, you have R1 plus Y, so plus it goes to Z, that means R1 out should be on. So again, that one out and goes here. Then you have to have Z out on and R3 in on. That means it goes added up, comes here, it goes through to the right register. RT is possible register transfer is possible with the one bus structure, meaning Ri, any register, or Y can get the contents of anything but Y. Since result different from operand, it cannot go on the bus that's carrying the operand. So you can only have, in other words, what we are saying, you can only have one piece of information or content of one register on the one bus. If you have only one bus available to you, you can only have one piece of information. If you put another piece of information, they all gets garbled and you get just junk. There's nothing right over there. The ability to begin with an abstract description, then describe a hardware design and resulting concrete RTN and control sequence is powerful. We shall use this method in chapter 4, as I have discussed it. We're going to use this model. You're going to get into the detail of this information, how we're going to use this information to show you how we're going to design the processor. Now, in my next lecture, I am going to basically, my next lecture probably will be next week. And I will go over the homework problems and some other problems. The only thing I will do next week and also I may discuss chapter 3, but it won't be in your exam, okay? And so next week lectures will be the homework lectures. I'm going to solve the homeworks and some of the homework problems. And also I may cover part of the chapter 3, because chapter 3 is not really, it's only one part of chapter 3 is part of our course. The rest is not part of our course because it talks about the specific computers, which we are not interested in that. So next week it will be chapter 2, homework from your homework problems that I will discuss, and then some other problems I may solve them in class that I haven't discussed that I haven't assigned to you, but I will solve those problems, and then I will also try to discuss chapter 3. All right, I will see you in next lecture next week. We have plenty of lectures for this week, so you should be fine, and I'll see you next class.